Okay, so here we've got, if you remember L-DOPA, this is where the pictures come in, because L-DOPA, the neurotransmitter dopamine, remember? Benzene, the face, right, in the ring structure here. Double down, you got a nitrogen, the double bonded O. Remember, this was his little mariachi thing. He's shaking at the end, he's shaking his oxygen. This is Capacian, the pepper. I know I'm not pronouncing that right, but what you do, here's a little trick. Who cares how you pronounce it? If you pronounce it the way it's spelled, then at least you can spell it or type it in and look it up. People learn how to pronounce it. Well, a lot of times the pronunciation isn't the way it's spelled. So you're better off, even if you sound ridiculous, say it the way it's spelled. So I called it Capaicin. Hold the Acin. This is cayenne pepper in the purest sense, okay? They're finding these have biological properties to them. So when we look here, what we see, my color coding again, the double bond on this carbon chain here. Double bond, bound, 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 bound. Isoprenes. Remember the isoprene structure we were talking about? 5 carbons long. This just happens to have 2 methyls hanging off the end here. So if you picture this, this is going to have something that doesn't like water down at the bottom of the tail. Up here, even though the benzene ring doesn't like water, what do you got? You got an OH alcohol. You can't see it here, but you got an ether, they'll call it, an oxygen in the middle of another carbon chain. You got nitrogen, oxygen here. So some of this up here can, interact with water. This down here, totally hydrophobic, as they'll call it. But what you see now is a real similarity to the dopamine. And what do you say? L-DOPA, give him a little sombrero. Same ring, same oxygen's coming off, same 2 carbon away, well, 2 spaces away, you got a nitrogen. And next to that, the double bonded O. Really close to dopamine, L-DOPA. Say that here we've got citric acid. Now this is going to be fun because when we see how glucose, 6 carbon chain long, forms a ring when it's in aqueous solution like your blood, but it's just 6 carbons straight. When the mitochondria, this is why the mitochondria are so important, they break down the sugar to get the ATP, all that boring stuff you heard about in biology. It's really cool stuff. But the citric acid cycle, they call it, I made the citric acid seagull. See the carbon. This is why organic chemistry, carbon. Look at this. Carbon, remember the double bonded O with the single OH? Well, forget that notation. These oxygens are the same distance away. Got a carboxylic acid out here. Water loving, electronegative as all can be. Carbon to carbon, usually go by 2s you count. These are called betas. So you got a beta carbon there. Here's 2 carbons here. 1, 2 with another double bond carboxylate out there. 2 carbon. 1, 2 carboxylate. So look at this here now. You've got carbons, and this really is a carbon skeleton because if you picture a bird, you got all the bones on the inside. There's the carbon skeleton. What do you got on the outside? The oxygens. So the citric acid seagull. Again, this will come in handy because when you look at any of the posters showing the Krebs cycle, the citric acid cycle, glycolysis pathway and all this stuff, I couldn't follow it. You got a double bond here going to an O, you got an O here to a double bond, they're just moving stuff around. But when you see a seagull turn into a lactate acid tiger, so another product through the glycolysis, glycolyzing, we've come up with the Pyruvate Tiger, okay? Again, the carbons, black, carbon, oil, all that coal is black, so we'll just make them black balls. We've got green for the oxygen, so we got a double bond here. We've got a double bond to an oxygen up here, single bond here. That's what that carboxylate was, so these actually should be the ones that are the same distance. See here, this is why we draw two different structures to show you. You've got the carboxylate tail out here, the one like the fin the bee fish was doing. Double bonded O here coming off carbon. So you've got one carbon, two carbon. When it's nothing out there, that's a methyl group. So where's the methyl? I turn this around, give them a methyl tail, two carbons on the body. So 3 carbons, this is half of what the glucose was. So when you split glucose up, you get 3 carbon things going on here. The OHs, they'll call them alcohols because sugars are alcohols, if you believe it or not. All these carbons are going to start having oxygens hanging off the end. And do you notice there's no nitrogens involved in this? It's getting late, I'm starting to stutter. Nitrogens. There's no nitrogens in sugars. Proteins have the nitrogens. This is a fun one. Tryptophan is a precursor to the dopamines and L-dopas and stuff. Hey, that's something we got to do. We got to go back and look at this. Anyway, we got the face here. This is one of my early drawings to make this really simple before I thought I'd go too far overboard with the cartoon. Benzene, do you see the face here? Aromatic 6 carbons structure. Here, a nitrogen in there. So give them a little nose, a double bond to the nitrogen. This is going to have an arrow structure to it later. You're going to have the O8 O's on the end and the nitrogen on the front. It's going to be the arrow, just like through the head of Steve Martin on the Paba. So what do we got here? We got a nitrogen in a ring, 6-membered aromatic ring. You look now, it's so much easier to see. And the beauty, that when you remember tryptophan, of all the codons, there's one code for tryptophan. There's 3 codes to stop. One for tryptophan, UGG. I'll give you a hint. Tryptophan is an essential amino acid. I couldn't come up with a real cartoon for it, but I thought we just got to give it some kind of life here, right? We've got the 6-membered ring. 2 of them are nitrogens. It's aromatic to the hilt because of all the double bonds in it, right? You got a methyl hanging off here. You got a amine up there. So this ring usually is bound right to another ring. This is bound by a carbon in between it. And where does it bond to? See, there's 2 nitrogens here. Nothing's bound to that. Remember before I was saying how cool it was that the nitrogen was holding the methyls? These nitrogens have nothing. There's an amine and a methyl on there holding into the carbons. Here, the penta ring, the 5 members, is bound by the nitrogen to a carbon intermediate, and there's a sulfur in it. This is the coolest structure I've seen when it came to the vitamins. So they call it vitamin B1. It's also got a name thiamine, okay? But I thought the way I'll start distinguishing these, because even though I know there's a cartoon, I didn't have a name for this one because it's not really a cartoon. If you see here, I gave them, eyes and kind of tried to make it look like 2 of them floating off together. But what's cool is the sulfur in this ring. You've got a sulfur in a 5-membered ring. Sulfurs are humongous. Remember the periodic table? It's underneath oxygen. Same oxidation state as an oxygen. But you've got a sulfur in a ring. You got a nitrogen with 4 bonds that you usually don't find, so it gives it kind of a plus charge, delta plus. Delta plus. Methyl hanging off that ring, and ba-boom, ba-boom, 1 carbon, 2 carbons OH, that would be an ethanol. That's a real alcohol group. They'll call the alcohols just the OH, but ethanol is 2 carbons. So you've got an ethanol